just like people in the Saints visiting locker room apparently. So, anyway.
Wait.
There's the story that broke yesterday that the general manager of the New Orleans Saints basically had wiretaps on the opposing coaches during the game. He was like listening to their conversations during the game and stuff like that. Allegedly.
They still have very good technique.
All right. If you go to the back side of the problem set that I gave you on Friday, the front side of the problem set I gave you, the front side of the problem set is the friction problem, and we did an example of that on Friday. A couple more problems on there are very similar to the ones we did. Yesterday, the top of the back side, we did the bank turn, where we talked about how the normal force comes tilted, and then one component of the normal force points towards the middle. That contributes to the centripetal force. Today, we're going to talk about tension. Ooh. In the big picture, tension is really pretty easy. It's just like a string that prevents an object from going in a straight line, which we sort of started this demonstration with the ball and the string that we did at the beginning way back last week. But now we're going to put some numbers on it. So let's start with number 1. So number 1 says, a box with a mass of 1.5 kilograms is attached to a string with a length of 0.8 meters. The string has a breaking strength of 500 newtons, meaning it will break if force 500 newtons applied to it. The box spins in a horizontal circle on a frictionless table. What is the maximum tangential speed that the box can spin without breaking the string? So, starting off, what are we looking for? We're looking for tangential speed, right? That's our unknown. Things that we have to work with. They gave us the mass of the object that's moving around in a circle, the 1.5 kilogram box. They told us that the length of the string is 0.8 meters. That gives us the radius. And then they also told us what? The breaking strength of the string is going to be 500 newtons. Why is that important? Joe, go ahead.
Because you're going to use that to solve for the velocity.
Because if the string breaks at 500 newtons, what is 500 newtons going to show up as in our problem? The 500 newtons is going to show up as the centripetal force. Because what is the string doing here? Well, the string is going a circle, but it's doing what?
Pushing it.
It's preventing the box from going in a straight line and making it go in the circle. So if the string breaks at 500 newtons, that means we can have a centripetal force no greater than 500 newtons. Okay? If we go through and do this, we said that all of our problems start like this, right? F of c equals something. In this case, right, where is the centripetal force coming from in this problem? What's providing it? The string. So that means that the centripetal force is equal to the tension force. Tension just being that fancy name that we call a force coming from a string. What do we know about the centripetal force? How do we calculate it? Hopefully you remember the formula by now. mv squared over r. And then we just went through that discussion of what can be our maximum tension force in this problem. We can only get up to 500 newtons because that's when the string is going to break. From this point forward, right? Do we know the mass? Yeah. Do we know the radius? Yeah. We can figure out what V is. Carry on. else verify for me 16.3? Okay, good. As long as we've got 2 people. Second. All right. Are we good with this? Okay. This one gets a tad more complex. So do with that information what you will. So it says, 2 masses, M1 and M2, are connected by a string and rotated around a fixed point. M1 is 1 meter from the center of rotation. M2 is 1.3 meters from the center. M2 moves with a tangential speed of 1.0 meters per second. So, A says, what is the tangential speed of M1? Okay. So what are we looking for? Tangential speed. There's a couple ways we can go about solving for tangential speed. Okay. First, we know that it shows up here in this formula for centripetal force, right? And we've done that a couple of times where we've figured out what the centripetal force is and used that to solve for the tangential speed, if we know the mass and the radius. But we also talked about another way that you can figure out the tangential speed. What's another way that we can figure out the tangential speed? You actually used it on your quiz that you handed back to me yesterday. We can also figure out the tangential speed of something by taking the circumference of the circle that it goes around and dividing it by the period, or the time of one rotation. Okay. If we start looking at things that we have to work with, right, what do we know about M1? Okay, we know the mass of M1 is equal to 2.5 kilograms. We know the radius of M1 being 1.0 meters. Okay. Do we know anything else about M1? That's it. Does it look like we're going to be able to use this equation here? If we did, we'd have to know what? What else would we have to know in this equation to solve for V? We'd have to know the centripetal force, and really it doesn't really look like it's giving us anything about the centripetal force. Okay? Just to be thorough, let's go through and let's talk about M2. So we know that M2 has a mass of 3.5 kilograms. M2 has a radius of, where is it? 1.3 meters. And then it also tells us that M2 has a tangential speed of 1.0 meters per second. Okay. We can definitely use these things, this information here, to find the centripetal force on M2, which actually gets us more into B, which is fine, okay? Let's keep that in mind for later. Let's stick with A for now, though, okay? All right, something that's going to be important here, okay, that we haven't really talked conceptually about, but we'll talk about it now. Okay? If those 2 blocks are connected by a string, and they're moving in a circle, how much time does it take M1 to complete a circle versus M2 to complete a circle? It has to be the same time, right? If they're connected, right, and they go around the circle, they have to complete one circle in the same amount of time. If we go back to this equation to calculate the tangential speed, do we know the radius of M1? We do know the radius of M1. Do we know the time it takes for M1 to go around the circle? We don't. But we know that it has to be the same as the time that it takes M2 to go around the circle. Does that make sense? If we apply that here, do we have enough information to solve how long it takes m2 to go around in the circle? We do. They gave us the tangential speed, so that'll go 1 here. 2 pi is 2 pi. They gave us the radius, so we can figure out what the time is for one rotation, which because it was called the period. Go ahead and do that real quick. What do we end up with? Is that anybody else second? All right. So we said this time for one rotation on M2 has to be the same time as one rotation on M1. Now do we have enough information to figure out the tangential speed? You do. So if we take v is equal to 2 pi times 1, because that's the radius of M1 circle, divide that by 8.17, that will give us the tangential speed of M1. .77? Anyone? Yeah. All right. Good there? That makes use of some of the ideas that we introduced earlier with calculating tangential speed by taking the circumference and the period. Okay. Now let's apply that to some centripetal force things. I am going to take this problem and I'm going to put it on a new page, so we have some space to work with here. Okay. And let's talk about B. It says, what is the tension in each string? So we need to know tension in string 1 and tension in string 2. Let's talk about string 2. We've already established some things about block 2. We know the mass of block 2 is 3.5 kilograms. We know that block 2 has a radius of 1.3 meters, and that block 2 is traveling at a tangential speed of 1.0 meters per second. And Katie, we said before, with these three things, what can we calculate here? We can calculate actually the centripetal force, which is being provided by the tension of that string right there. Okay? So let's do that real quick. The centripetal force on block 2 is equal to the tension in string 2. We know that this is mv squared over r. We're trying to solve for the tension in string 2. We know the three things. We know m, we know v, we know r. So we can figure out what the tension of string 2 is. What is it? Okay. Good there. Okay. trickier. And, alright. Here is block 1. Okay? Here, hold on one second. Okay, here's block 1, and here's block 2. It's a little bit bigger, so I'll make it a little bit bigger. We just calculated that block 2 is feeling a force of 2.7 newtons like this. Yes? Because if you look at its position in the picture, right? If it's at the very top of that circle as it's drawn, the centripetal force has to point towards the middle. There's the middle of the circle. Ooh. Forgot I was arrowing. There's the middle of the circle. That means that M2 has to feel a centripetal force in this direction. Yes? Okay. Here's where it gets a little trickier. M1 has to experience a force in this direction. Yes? Everyone see why that has to happen? Because if we look at the picture, right? M1 going in a circle, middle of the circle is right here. That means M1 has to experience a centripetal force like this. However, that's not it. Okay? This blue arrow comes from the string connecting M1 and M2, right? Newton's third law, which we learned a while ago, right? What's the gist of Newton's third law? Equal and opposite reaction. So this string connecting these two is applying a force, at least in this picture, downward on M2. But if it's applying a force downward on M2, what also has to be going on?
Upward.
Upward, where? In the opposite direction. On which object? Come on.
There you go.
So,
Oh. Chop.
That's 2 up, of course.
okay. We said that there has to be an equal and opposite force. So this force has to go this way,
Whoa.
right? But we said that one thing about action-reaction pairs, they always have to be on different objects, yes? Does that sound familiar? Okay. They don't cancel each other out on different objects. I know it's a long time ago, but wow, I see a lot of blank stares. However, so tension is a two-way street. If one side of the rope is applying a certain force, the other side of the rope is applying the same force to whatever it's attached to. Right? That means that if this block is experiencing a force of 2.7 newtons this way, M1 has to be experiencing a force of 2.7 newtons in the other direction. Okay? Yes, no, maybe. Got a couple of yeses. Didn't get any no's, so I'm gonna go. All right? All right. So this is the tension in string 1, which we don't know yet, which we're trying to find. Going back to your quiz you just turned into me, one of the short answer questions said, is an object moving in a circle accelerating? And the answer is yes, because it's changing directions. If an object is experiencing acceleration, what else does it have to be experienced? What causes acceleration? A change in velocity is acceleration, but what causes it? A net force. So that means here, the net force acting on this block has to be equal to the centripetal force. When we do net force, what do? Add the forces. So we have the force of tension 1, that's the purple arrow, plus the force of tension 2, that's the blue arrow, has to together equal the centripetal force.
Wait,
I know. So I like when these things come together.
scroll up a little bit.
Okay.
So you're saying that the pull from M2 goes on to M1 somehow?
Because just if you have if there's something you're good.
Ooh,
Right now.
the big guns.
You can actually get rid of this. So. All right, so grab that. Okay. So pull the blue one so that it applies a force to the red one. Keep going. Keep going. Okay. Can you feel the red one pulling back on the blue one?
Yeah.
You right?
I didn't know they were connected.
They are. Yeah. Do you see? Well, if you had your picture out in front of you, you would be able to see that it was actually connected. So. Yeah. There's like here. See? Excited and sassy. I'm just in a whirlwind of emotions.
Okay.
So yeah, there's a string connecting those two. Okay.
Okay.
All right. Does everyone see where I got this from? Where we ended up at this point? Okay. We're looking for the force of tension 1 plus. We know the force of tension 2. It's 2.7, but which way is it acting on M1? It's acting away from the middle. So is it hurting centripetal force or is it helping centripetal force? It's hurting centripetal force. So what do you think we're going to do with it? Make it a negative. And together, they have to equal the centripetal force, which we know is equal to mv squared over r. Do we know the mass of block 1? We do. Do we know the velocity, the tangential speed of block 1? We figured it out in part A. Do we know the radius of block 1? Given to us in the problem. The only unknown we have left in this equation is the force of tension 1. Conceptually, right, if on this block we have one force that's pointing away from the circle and one force that's pointing towards the middle of the circle, which one's going to have to be bigger? The purple one has to be bigger because that one is how we make something go in a circle, right? It has to be bigger towards the middle than away from the middle. Solve. It was actually a good day to record. No, because in this, Tom, in this case here, we're still only talking about the force acting on this block. So when we do that mv squared over r, it's just the mass of that block. The forces is the only place where we have to do the combination of what's happening to it. Yeah, so when we're calculating the centripetal force, it's still just the mass of that object moving in a circle.
It's going pretty good. We all are.
Give me it, I'll do it.
Ishmael, do you even feel like, are you still in school?
Yeah, we're still recording class, so. And you're real close to the microphone, just so anything you say is probably going to get picked up.
Say something.
All
Platypus.
right, we good there? There is one more problem in the tension section that deals with some angle type stuff. Tomorrow, like I said, we'll do another friction practice problem. We'll do another bank turn problem. We'll do another tension problem as well. Then we'll start getting into the vertical circle and start incorporating gravity into this whole discussion, which I know is what you're all waiting for.
Come over here, Jamie.
No, no.